All right, so thank you guys for all coming out. My background is kind of all over the place, but financial data sets have been kind of where I've spent most of my modeling time, and that's actually going to be the bulk of what I talk about today. We're going to hit 2 case studies. I want to get more applied. I will not go toe-to-toe with the great theoreticians here, but hopefully I'll give you some ideas of what we can take away. Do I have? Here we go. So specifically what we are talking about, you may have read this abstract, you may not, but basically we at Fiddler Labs have been working on explainability technologies kind of in a very applied sense. We're trying to productize them and make them useful to more people and easier to use, as well as kind of getting away some of the gotchas or adding features where we can. So today I'm going to talk about primarily one major case study, which is sort of fair lending. And I will say, even though I've modeled financial data sets, I haven't worked in the regulation space. So any of you have, please forgive me for making some abstractions or simplifications. And then we'll also talk about a more medical case, present some other research that is actually not mine, but is something we've been looking a lot into at Fiddler. And so hopefully the goal is I want everyone here to be able to take away some ideas about explainability. If you're new to the space, hopefully this will be a great primer. If you've already been in the space, hopefully there'll be some nuggets of wisdom. And if you're already practicing it, hopefully there'll be a couple generally used guidelines or things you can take back to your own practice. And here we go. Okay, so really there are 2 big takeaways I want to give you guys. The first one is that explanations are kind of just models in and of themselves. And so if you're used to building models, building explanations is kind of related more than you'd think. And the second one is that there's a great power to this idea of global complexity yet local simplicity when it comes to explaining complex phenomena that are globally complex. And so hopefully by the end of this you guys will have a much better understanding what these are, but I want to put these up first so you can kind of percolate on it as I talk. So to give some context of why explainability, I think that's a question I get a lot, and I want to kind of preempt that here. There's some concerns today. Machine learning used to be applied to ads or other cases where we can test really quickly. If you show somebody a stupid ad, like it doesn't really affect their life drastically. The stakes are not so high. Now this technology is maturing. It's being applied more and more to cases where people really care about the outcomes. Discrimination is a big word that's popped up with AI, and unexpected consequences. Once you push something into production, you're affecting real people's lives, you're affecting your business's bottom line, and you're doing it in a way that maybe you want a little bit more trust and insight into. There's also legal backlash now that wasn't there before. Now here we see a tweet where the hashtag AI is next to kind of fairness and your rights. And GDPR. So, even though GDPR is still being interpreted and developments are coming out, we see that, you now have a right to an explanation whenever there's an automated decision about you. And if AI is being used in this automated decision, we have to be able to explain how that is playing its part. So that's a big, case of how do we address this AI explainability. I'm going to talk now about the takeaways that hopefully really break that down further. So first here, what I mean when I say explanations or models is that when you have a phenomenon you're trying to explain, maybe it's a model decision, maybe it's just a real life phenomenon, that explanation is sort of in the form of outcome Y happened because of some input, features, reasons. You have it X. And then if you're a math person, or even if you're not, this is pretty simple. Sorry, I don't have any of the probability, really complicated sigma notation today. It's just going to be like simple equations here. But we see it's kind of y equals f of x. And then here you can read that a different way. The way that x turns into y is some function. There's a list of rules. And so that leads us to this idea that, of course, we just have to look at the model and we understand why it's doing what it's doing. Except you run into models like this. This is a 3-layer neural network. And if we have any volunteers, somebody go ahead and read this equation here. Anyone want to give me an explanation of what's going on? No, so we have these activation functions on top of activation functions, on top of weighted sums. And of course, you can compress this with tensor notation or linear algebra notations. But at the end of the day, then, do you really understand the linear algebra notation in an intuitive way? Some of us might. I personally have more trouble with that sometimes as a practitioner. So black boxes are really just models that have rules that are so complex that inspecting them becomes a challenge in and of itself. And to solve this, when we want to put it into practice, we have two really kind of approaches we can take. The first one is to abandon complex models, or to construct their complexity in such a way that we can break them down into smaller pieces, each of which is meaningful, and we can interpret that piece alone, and then kind of aggregate our interpretations as well as aggregating the models, and really get that kind of inspection-based approach. And that's been, I think, the predominant theory of interpretable machine learning for many years. But I think recently there's also been this other trend toward, can we approximate complex rules with simpler ones to get a pretty good understanding of really what's going on here in a way that's good enough, understandable enough, and lets us keep our black box. And so, these are kind of two different ways. I'm going to actually spend a lot of this talk, arguing for black box explainability, not because that's every case always the best. I'm a practitioner, I use what works, but because there's some compelling reasons to go after this, and I think also this is something that more people would be better off learning about here, because there are some interesting nuances and takeaways. So, three big reasons I have here: poor performance, potential for discrimination, and my personal opinion, with no citations here, I think this is just more of a kind of human-based, intuitive way of doing it. So if you go on Kaggle, you'll see that the winning solutions are typically ensembles using black box models like boosted tree algorithms and neural networks, and none of those is a simple interpretable model in and of itself. And so, this is the playground in which the most, powerful, most performant model wins, and we don't see a lot of these simple interpretable models. So there's often a trade-off. In terms of discrimination, an overly simplistic model can kind of, depending on your data set, and there's some really interesting research by Irene Chen on this. You can have, if your model is maybe a line and you're fitting it through a nonlinear space, you may fit the non-outliers better than the outliers. And sometimes in the real life situations, the outliers are protected classes. They're minorities. They're people who lie away from the typical groups, but should not be treated any differently by your model. So if your model is worse at doing what it does, approving loans, giving medical diagnoses, predicting criminal recidivism, and it's overly fitted to kind of the majority class, there can be some interesting discriminatory effects that you don't even realize are coming in there. So even though you're okay with sacrificing performance, you may run into other problems. And then lastly, I want to kind of give a humorous example of why I think black box explainability is sort of a human process. How many of you have had, let me read the pictures here. You wake up in the morning, the alarm's ringing, and you have a question. For me, this is usually, do I want to go out and pick up some heavy things, or do I want to roll over and kind of take a cat nap for another 45 to 60 minutes before I start my day? This is a decision I make quite frequently. Almost every morning, my alarm goes off. I decide one or the other, and I have a vested interest. I want to do more of the bottom choice. I would like to be a healthier person, eat right, do all these good things. So I want to explain what goes on in my head when I, pick the first option. I want to explain those decisions. And I can come up with, so many different models, excuses of what's driving that behavior. I can test them out and see. And if my friends ask, I can convince them perfectly. Oh, it was rainy. I was up late the night before. I was still sore from the last time I worked out. But in all those cases, there's no MRI imaging. There's no brain scanning going on, really figuring out, is that really how Luke's mental model works? You're just kind of fitting something, looking at my behavior, looking at every day I do these things, and picking out patterns of, okay, when the inputs look like this, the outputs tend to look like that, and that's why. And I can come up with some simple rules of, like, it's raining, I go to the gym less. Well, is that actually what's driving my decision, or is that just a very good explanation? I would argue that this kind of black box explainability has its merits. And so this leads us to kind of another benefit to this black box explainability, which is my second takeaway for the day. And this is the idea that you can be complex in your decision making, in your model, but for a specific decision, for a single inference of a model, you can be quite simple. And to give credit where it's due, this is an image popularized in the paper that presented the LIME algorithm, locally interpretable model explanations. And a lot of these ideas, I think, were first at least popularized by that work. But the basic idea here is that for, let's say, we have a single prediction. This is, your loan application was rejected. So red is bad, rejection. And this is, input x1 and x2. Our model is this color. So you can see, okay, for any x1, x2 pairs, like if we knew the model perfectly, anywhere it's red, we're going to reject. Anywhere it's blue, we're going to accept. It's a nice model. It's also not very linear. There's not a clear explanation of, okay, if x1 is, greater than this amount and x2 is that way, then, accept or reject. However, around this decision, we can draw this linear line. We can now say, okay, around this, if you had, a higher x1 value, you would be accepted. If you had a much, if you lowered it, you'd still be rejected. If your x2 value went up or down, it probably wouldn't do anything for you. And so we can build this local explanation that is kind of accurate for that particular example and really meaningful and fits the question. So this is my rainy day example. Okay, if it's not raining, maybe there's other reasons that are driving sleeping in. But here, for rainy days, it becomes very simple. We can get a simple explanation, pass it to a person, get everyone on board and have everyone understanding what's going on. So this other, idea of global complexity, local simplicity. Sometimes explanation can be a matter of finding a local area where we can achieve the simplicity needed for explanation. And so with that, I'm going to jump into our case study, where I'm going to actually present this mentality and approach in the wild. Today we're going to be focusing on the idea of loan applications. If you have applied for a credit card, like ever, you fill on a web application, you submit, there's a little loading circle, and you get a response almost immediately. And the reason it's so fast is because not a single person is involved in that decision. What happens is your loan application gets sent as some sort of JSON blob to their server. They process out a vector of machine learning features, feed that through some model that they've already trained, and get back a score. In this case, it might just be estimated risk of defaulting on the loan. It's probably much more complicated, maybe multiple scores. They have a hand-designed set of thresholds. But they're going to look at that score and automatically make a decision based on it to accept or reject. So here, if you have a 30% chance of default, which is expressed in probability units here, they're going to go ahead and the lender will reject this application. Now, in real life, this is a problem that banks deal with every day. Fair lending laws require lenders to explain their rejections. If you give someone a loan, you do not have to justify yourself at all. But if you reject somebody, you have to submit justification and reason to be able to say, okay, it wasn't because this person was in a neighborhood, a specific neighborhood, and I'm redlining against them, and that neighborhood might be majority minority residents, and there might be some racial disparate impact. No, it's rejected because their credit score is too low, or some other thing that we've considered as fair. So explaining that, the way the model uses its inputs is important, because if it uses it in a way that's not understandable, we have no explanation. So the other problem with this, though, is they can't just come up with a very simple model because they care about performance. The bank makes their money on having a good credit model that has a good accuracy. If they accurately predict somebody's risk of default and they lend to the people who have a low risk of default, they're going to recoup higher investment returns. And then, like I said, they have this requirement they are interpretable, and so we also need a person to be able to go, aha, I understand what the black box is doing. So to set the stage, here's some details on the data set we used. It's about 500,000 peer-to-peer loans. These were from Lending Club, public data that we've processed to include just features that represent kind of information available at the time of a loan application. And then the target is whether the outcome was fully paid or charged off. Charged off is just a fancy word for the bank gave up. The lender gave up and they charged it off as a loss. In this data set, at least in the training set, there's about 13.5% charge-off rate. We have about 50 continuous variables. Many might be integers or not so continuous. Here's some examples of selected ones. You have the amount of the loan, the employment length of the person, their annual income. If you can't read some of the small text, don't worry. The important stuff is more on the left. We have some categorical features. If we want to hunt and code those, we get a bunch of these inputs, over 100 model inputs. And because we're not in the business of actually creating lending models, we just threw them all into these 2 different algorithms, trained them on 134 indicators, and looked at the performance. So we chose a simple model, a logistic regression, a complex model, a gradient boosted trees model. And we observe, although it's hard to tell from this ROC curve, that there's a significant increase in performance when you use the more complex model. So there's a trade-off between the simplicity and the performance of it. Specifically, I mean, you can look here, like let's say the bank is I'm standing right in front of the light source. This may have a laser pointer actually. Anyhow, all right, I'm not going to worry about that. If you were to accept a 60% false positive rate, you might be seeing a % or 2 increase in the true positive rate, which is the rate at which somebody is being rejected because they're risky. So if we catch 1 or 2% more of the people who are going to default on their loans, that cuts 1 or 2% of our overall costs, which is huge to our bottom line. So with that in mind, we're going to go to the interpretability section. Logistic regression has built-in global interpretability thanks to the fact that it's a linear model and by construction assigns importance from its weights to each input. So here I've written out in kind of some linear algebra notation, we have log odds of the event, which is a default in this case, is equal to a weighted sum of inputs x. And then we put it through this transform that turns log odds into probability units. And this is a logit link function is responsible for that, or sigmoid. And then we can kind of interpret what this model has learned by looking at the weights. So what is WI? Well, since we standardized our input, which I didn't mention, but we did, we can sort of compare the magnitudes in some wishy-washy hand-waving way, and we can definitely compare the directionality. So we can see total accounts has a negative weighting, so the higher your total accounts, the lower your log odds are. And then when you put it through the sigmoid, the lower your probability is going to be, because it's a monotonic transform function. Conversely, if your debt-to-income ratio, DTI, which is the second orange thing there, the higher that goes, the more there's a weighting that weights your log odds higher. And so you have problems with, if you have very high debt or very low income, that'll show up as a high DTI, and then you're going to have the model will assign you a higher risk. It's important to mention, though, that you can't just say, okay, well, if they pay off some of their debt, then it'll change this much, because that'll affect their debt-to-income ratio. It'll affect 4 different measures of different kind of debts, depending on what debt gets paid off, some of these other features. If they close out certain rotating revolving balance accounts, that'll change the number of open accounts. It'll also affect their FICO score, which is included here as FICO range midpoint. We actually don't have the exact score. We have a midpoint of a range of scores they fall in. And so, there's some, even with this perfectly interpretable white box, glass box model here, the fact that we have correlation between inputs, or inputs are actually functions of real world events, because there's engineered features like debt to income ratio, and the fact that we put it through this nonlinear transform means that there's a little nuance, that we can kind of get directionality and maybe magnitude, but this has been good enough. In the lending industry, generalized linear models are very popular, at least where I don't work at a bank. They may be doing something slightly more sophisticated with monotonically constrained boosted trees or something like that. But here, this monotonic functionality and the weighting is good enough to generate very satisfactory explanations that have stood the test of time. Boosted trees, too, get some sort of importance weighting. We can look at their cumulative information gain from the training process, or some of these other features that people have proposed, counting number of splits by feature, and get a sense of, like FICO range midpoint was used a lot to generate a lot of discernment, kind of reduce the entropy of the prediction task in the base learners of this model. And if all that sounds like gibberish, well, it kind of is when it comes to determining what caused the model to make a decision. And that's what we care about when we go back here. In this particular case study, and this is maybe a bonus takeaway, it actually depends what you're explaining as how the best way to explain it is. So here, we really care about why they were rejected, which in this particular case, we're going to say, well, they have a threshold if their likelihood of default was above 20%, 0.2, and remember the base rate is about 13.5%. So if we predict they're at 20%, they're almost, they're approaching double the base likelihood. They're much riskier than expected. Why does the model think that? Well, that's the rejection, and we need to explain it, why the prediction is significantly above the average here. And so here's a case where you can see logistic regression and boosted trees. Predictions is the second to last two columns, or sorry, the columns that are third to last and second to last, and then the actual result. And we see that it's sort of calibrated, but we really want to dig into this. And so with logistic regression, it's pretty simple. I have a zoomed in version here. So walking through it, you can see the factors. We process the factors with one-hot encoding and standardizing, so they become these indicator features that get fed into this massive linear algebra that is a logistic regression fit. And then if we multiply the weights that we saw before on that slide against these indicators, we get some sort of impact. And so we have a base log odds, that's the intercept of the model. It's about -2. We run that through our sigmoid, we get about 12%. Which is very close to the base, 13.5% default rate. That makes sense. Then when we sum up all of these facts, and it's interesting, we can see that the first two things, the fact that they're employed for 5 years and have a bunch of open accounts, actually contribute very heavily to reducing their log odds. However, kind of death by 1,000 cuts, they have a bunch of these other pretty high impact, modern impact features that, it's a very high loan, $23,000, which if you look at the distribution of all loans, most loans in this data set are much lower than that. Their FICO score, again, not high enough. Some of these things, they have accounts that are open past 24 months is only 7. It's got a impact on that. They have 7. It's a negative impact, and so you can start to see some of these things increasing their risk. But as the model, we can then just add the sum of this last column. All the way past, this is only the top, I think 10 features. We can sum it all up, it comes to about 0.75. We add that on, we move from -2 to -1.26, run it through our sigmoid, and we get our 0.22 out. And so when we explain something, we can say, okay, well, if you were able to raise your FICO score, you would have a decrease that FICO score impact on your log odds, which would then decrease your prediction. You'd probably get below the 0.2 threshold. Now, remember what we talked about, things you do to improve your FICO score might also change some of your other features, and then, that might add some complexity, but there's sort of an intuitive breakdown, and we can create an explanation. The real question is, can we match this for the boosted trees? Because if you just say, oh, well, the feature importance, FICO score was just really important. They go, well, how? What do I change? How do I get my loan approved next time? We're going to use something called additive feature attributions. This is a local modeling technique that kind of brings in this idea of local simplicity. So this general idea of this class of basically linear explanation models, where even though your real model is a really complicated boosted trees model, remember that explanations are just models. And so we can constrain our explanation to be of this linear form, where we have some intercept term, and I apologize for the Greek. This is the notation used by Scott Lundberg when he presented this general class, as well as the SHAP algorithm, or shape. I actually do not. Somebody can tell me afterward the proper pronunciation. But it's from the Shapley values of game theory, and how to fairly attribute the outcome of a game, the success, to the collaborative players of that game. And so if we think the outcome of this prediction game is the model prediction, or more nuanced, the increase in model prediction over some baseline, then we can attribute that to all of some set of features. We're going to actually pick different features. So we call G, this is just our explanation, because explanations are models. And we construct this vector that might simplify our inputs. Because remember, we had 134 inputs. Some were integers, some were continuous variables. We may choose to one-hot encode categoricals to get that 134, or we might leave them as categories. And so we make some of these decisions when we train our model. We can make different decisions when we explain it. That's a really cool power of this, because even a logistic regression on like genomic data, some sort of linear model can still have thousands of meaning. Basically, individually, the features don't mean anything. How do you explain that? Well, you might pick something else. For an image, you might choose superpixels. And I actually have next slide of a couple examples of these explanation features. But if we restrict our input, one of the things we can do is make them be binary. So we can say, okay, we're going to only explain in terms of yes or no things. So we can say, oh, this happened because blank was true or blank was false. It makes a nice human readable explanation. And so then this linear form comes out to be, the actual prediction, according to G, is there's a typical prediction that we would expect, and then we add this kind of blame for each of the input features that we're going to blame it on, where Z's are the reasons, and phi I is the blame for reason I. And so then I guess question that comes up is, okay, well, that's nice. This seems like a nice model. You can read it, you understand it, yes, no questions. How do you learn this model? And there are a number of techniques. LIME is a technique that learns a linear model. This paper by Scott Lundberg in the tiny font at the bottom presents this SHAP class as a unifying framework to unify deep lift, some tree-based methods, and LIME. And there's more work being done every day on these. So for this particular case study, we used Kernel Shop, which is presented by Scott Lundberg, his code, and we trained this model by kind of sampling permutation-based. Sorry, I'll stay on this slide. But I want to stress that, even if the assumptions underlying SHAP don't fit your data and all that, I think that the idea of these local explainable models is really the key takeaway and the important part. So here, just to give some ideas of what you can explain in terms of depending on your particular task, if you have structured data, you could just replace, for each input, if it's a continuous feature, you could just replace with the mean value. Or if it's categorical, you could place it with the most common value. Another option is you could permute a feature a bunch of times and say, okay, Zi is, let's say FICO midpoint is the feature I'm trying to blame things on. This applicant had a FICO score of 700. Knowing that their FICO score was 700 caused the model to do something. What did it cause? What is the blame according to that piece of information? Well, how do we simulate removing that information? We can permute it. We can run the model with everything else the same, replace 700 with a different number from another row in the training sample. And we can do more than one at once, because sometimes features interact. We can replace subsets with permutations and average them out. And that's kind of what this kernel SHAP function is doing. There's a kernel that weights things to provably, with infinite replacements, recover the Shapley game theoretic guaranteed values that are kind of fair in a game theoretic axiomatic principled way. Even if you don't run it infinitely many times, you just get a pretty good model that's a good explanation. For unstructured data, you can do things like, for words, you can do a bag of words model. And you can say, okay, we're going to blame it on the vocabulary of this input. And even though in general, bag of words models may not be an accurate way to describe your complicated deep neural network, for a particular input, this local model, very simple local model, may actually describe what's going on quite well. For a particular tweet about climate change, the word climate might be really important. And just being able to say the word climate was important for this example is a good explanation of what the model's doing. So we can do that, superpixels for images, that sort of thing. So once we've binarized our features, here, remember, we're doing this absence or presence of feature I is the I that we're explaining. And again, I realized I made two versions just in case the size wasn't big enough. Hopefully you all can see a little bit better here. We can run the model through a bunch of samples on the training data and see the average model prediction is about 0.14. Again, the base rate is 0.135 or 13.5%. We see this sort of makes sense to us. So then for this particular example, this is the same example that the logistic regression predicted 0.22 on. Here we're getting 0.299. About 0.3, the boosted trees really doesn't think we should give this loan. But why? Well, we can attribute blame to every feature. And rather than worrying about some link function, we can just do it in a purely linear way. So our base prediction is 0.14. Our actual prediction is about 0.3. That change, about 0.16, everyone following me, can be called, we just call that to be, via our explanation G, the decomposition for each of these features. So by running this algorithm, we get blame. Loan amount has the highest blame, and it really increased the score. So if we didn't know that loan amount was 23,000, we would expect our model to predict 0.067 less, or 0.068. I'll round it here. Similarly, FICO midpoint, and this number of, I actually cannot tell you what the BCTL is. If you work in finance, you might know. Those things are also contributing to the model's kind of confidence that you are a riskier person than normal. However, there are a couple things that the model is actually using in your favor. The high number of accounts. As we saw in the logistic regression, Boosted Trees also likes 39 accounts. It thinks that's helpful. And if you took away that information, you'd expect your risk to be almost 2% higher in this case. So we're able to kind of blame it on all these things and say, okay, if your loan amount was something else, we'd expect an improvement in your score, and there's an explanation. We give that to the person. They're like, well, I didn't get the loan, but at least I know what's going on. Everyone can be sort of happy. And so we at Fiddler are kind of taking some of these ideas and trying to put them into the hands of practitioners, even outside the data science team. And so, you can actually come up with a more, interesting user interface. This is some of the work we've been doing, trying to show you how, okay, we can give you kind of what if, slide the sliders around, see what happens to your output when you change the inputs, but also run something like Kernel Shop on your features and get these, linear attributions. So you can see, okay, accounts open in past 24 months is really, negative in this case. So looking at that. And so that's one way to do it. But for the case of diversity of examples, I'm going to move into another case study in which maybe black box explanations is not the best way, and show you kind of some of the maybe limitations or things to be aware of when you're applying these methods. So for here, we're thinking about model-enhanced medicine. So one example might be predicting death from pneumonia, or predicting after 30 days whether someone will be readmitted to the hospital. And both of these things pose a significant risk of what I call correlation is not causation problems, where the model will learn something that's correlated to the outcome, but that actually human intuition will flag as not the right thing to do when you're actually using the model. So if you're going to use a 30-day readmission model to prescribe heavier treatment to people who are likely to have a 30-day readmission and lighter treatment to people who are not, you might start, you run into issues of things that are attributed to non-readmission might be that somebody has this very severe medical condition that the hospital is aware of. So if the hospital knows you have asthma and you have pneumonia, for example, they're going to treat you very seriously and reduce your chance of death significantly. And if our model learns that, if you have asthma, that's a good thing for your chance of survival, and we should start kind of ignoring the people with asthma, sending them to outpatient clinics, we might get people killed. And so we really need to understand these models to a deep fundamental level, and maybe that kind of wake up in the morning and decide not to go to the gym explanation case is not going to cut it in here. Additionally, humans are the ones who are using these models. This is not a completely automated system. You don't submit an application, get an instant response. This is a doctor at the hospital caring for you and trying to get extra information using this model. And so our primary goal is human intelligibility. We also care that the model works, because otherwise we just shouldn't add a model to the equation at all. Trust in people entirely. But our primary goal is it has to be able to be used by a human to augment their current system. And so one very interesting and compelling approach to this is design kind of decomposable, add complexity to models without damaging their interpretability. And so generalized additive models are a really interesting approach to this. And this is largely publicized in this KDD paper that I've mentioned on the bottom, and slides will be released after this, I believe. So if you're interested in this, please read the original research. But basically, to explain what a generalized additive model is, it's a very unpopular, deep neural networks are sexy. Everyone loves TensorFlow, and it does some really cool things like telling cats from dogs, or detecting hot dogs. I think that was a really popular application as well. But here, deep neural networks are very hard to interpret, and a lot of the techniques have a lot of assumptions that I wouldn't want to trust my life on if I were in the hospital. Generalized additive models take a slightly different approach, where they're going to put a set of activations through a link function, much like a neural network, but instead of stacking layer upon layer of it, or doing a simple weighted amount, but with just one layer, like a logistic regression, they're going to learn a bunch of functions, base functions here, called f, that transform a single input. So here, this is an example from pneumonia risk score. The H function is related to some impact on log odds. So if this transform here, a common one is the logit link function, or a sigmoid, like a logistic regression. Instead of being a simple line here, like a logistic regression would be, the more you increase age, you linearly increase pneumonia risk, or vice versa. We've learned this, this nonlinear function. But if you look at this by itself, you can see, okay, I know deterministically the impact that increasing my age will have on the activation that then gets passed through this link function to get my odds as y, which is the risk of death from pneumonia. in this case. So here we can observe an interesting pattern where the model has learned, okay, as you get older and older, and you can also look at where the data lies and see, okay, a lot of the people in this data set are in kind of the 60 to 90 age range. In that 60 to 90 age range, you see this very clear increasing trend, but then once you hit about 90, actually, for those kind of people way out in the tail, there's actually a slightly lower increase in risk. And so a doctor might be able to combine some of their knowledge that's not represented in the data or the machine learning situation to understand that. So for asthma, it's very clear if you learn a relationship that says more asthma is better for your chance of death, that's very counterintuitive because asthma is a really bad complicating factor if you have pneumonia. The doctor can flag that and go, I understand. We treat people with asthma very seriously and we improve their outcomes. Historically, we should keep doing that even if the model is telling us that because we do that currently, they're not as much at risk of dying. So here, this is another way of thinking of this is a special case of a GAM is when you have a linear F base function. And that is just purely logistic regression. You can learn these functions transforms very well, and there's some also interesting work done into learning about interaction terms, where you can learn a function on the interactions and add that to your model as well for interesting interactions. But here, everything decomposes nicely into these visualizable, graphable base functions, and some of the performance results are very compelling on these medical data sets. I encourage you to take a look at this this paper if you're interested in that. And so here we see that yes, deploying GAMs might be a nightmare. There's no mature packages out there that I know of that are near what TensorFlow can do with neural networks, but in these particular cases, there are other approaches that matter. So with that, I'm going to conclude my 2 case studies. I hope everyone learned something about explainability, and thank you. I will be in office hours afterward.
Couldn't you implement those generative additive models using like TensorFlow or PyTorch by just like not using the loop with all the layers? You could just implement it simply using some of the basic constructs?
Yeah, so how it basically boils down to how you parameterize these base functions f, and then how you kind of bubble that up and optimize the goal. You're minimizing some loss function over this entire functional form, but you have to learn these base functions. So you could use actually a neural network of however many layers you want as each f. This paper, I believe, actually uses a boosted tree algorithm, completely black box, but only on this univariate relationship between f and f of x, and then a linear weighted function, which you can linearly weight in TensorFlow. You're completely correct there. To my knowledge, I have not seen an implementation of GAMs in a tensor library like TensorFlow, PyTorch, though.
Hey, so in a lot of the motivations here, you're talking really about sort of the business, maybe less modeler's use case, but more the business user's use case of explainability, preventing unfairness and whatnot. How do end users kind of feel about the current sort of outputs you have with like Shapley values and sort of these univariate statistics, or do you need to go a step further to actually show whether the explainability is correlated with things like unfairness or other sort of poor situations?
Right. Yeah, that's definitely a nuanced question. I'm going to try and give a quick answer here, and then we can talk for hours about this later. That's kind of what my company is really focusing on, that question. The end users vary application to application. In one case, Facebook just launched Why Am I Seeing This for their newsfeed because their users are very concerned about things like fake news or algorithms gone wild. And they want to build trust with the algorithms just by explaining them a little bit. So if they can give compelling reasons for why stories are chosen for newsfeed, their customers are happy, and I'm sure they've tested that. In other cases, you may need more rigorous criteria to evaluate your explanations and understand if they're valuable. And when it comes to fairness and unfairness, you may actually use other metrics aside from understanding models to do that. So that is something. However, you can, if you have an intuition of what's normal for a model to learn, and you look at what the model has learned, and you compare that, and you think the model might be correlating to some latent variable that protected attribute or something, then that is something that explainability can help with. But there are definitely nuances to that.
One question I have is, so the FICO score, that it's itself a black box from what I understand. So one of your inputs is something that's not interpretable itself. The interpretations I've seen, it's like your account history may affect your score here, but it may has a lot of ambiguity in it. How do you deal with not having interpretable inputs and then trying to have an interpretable output that relies on that?
Yeah, so this actually is you just made a great pitch for this idea of picking different explanation features than you use for model features. So FICO scores, probably FICO is looking at a lot of the same inputs that the model is seeing, like debt to income ratio, number of accounts, account history. Some of those features are making their way independently into the model next to FICO score. So FICO score might be kind of redundant, actually. It might predict the same things that our overall model is predicting, likelihood of defaulting on a loan. And so if we choose to explain and blame the model's prediction on a select set of features, then we can decompose the model's prediction just in terms of things that we can directly understand. Now, I mean, obviously that if you don't use features that kind of correspond closely to what you fed into your model, the matchingness of that explanation may be called into question. But there's definitely a lot of power you can do with that. So if we were to remove FICO score from the model's explanation, it would be able to show kind of attribute the model's prediction to other features that probably are correlated to FICO score, and you just pull that out of the explanation. And that's an approach that can work in this case.